Morning, calculus.
Morning, Doug.
How's everyone?
It feels like it's the middle of the week.
Ah,
You're hitting that. Yeah.
a lot going on. Finishing up classes this term. Heading into a finals week. Yeah, I'm very glad to have a little kind of extra time in calculus for a couple of days to not make you rush so much and help you get some things done. I'm hoping to spend a little more time with Simpson's rule today, and then maybe get a good start on the project. So you have sort of today and tomorrow, so that you can kind of just be done with it before you even leave class. To some extent, this project is a little. I'm going to help you more with this one. I'm sort of going to have to a little bit, but it's kind of a neat application. Awesome. Let's see. So, what time is it? 8:01. I did a kind of a hurried job in between all kinds of other things yesterday, getting your quizzes graded. And what I really did is, in the spirit of full disclosure, because I'm kind of buried, is I looked through them, checked obviously that your answer kind of matched, and I looked to see really quickly if there was calculus that led to it, because obviously every one of those questions could be, you could write the right answer down just by sticking it into Desmos. And again, I'm good on you, those of you who said checked in Desmos and so forth, because you should have known if your answer was right or not. And to that end, minus question 8, of course, I mean, I'd say your test is going to feel similar to that, except for maybe you're not looking at this right now, but the first one said, the integral from 6 to 2 of x minus 4 over 2x plus 5. I might, instead of just giving you that question, and on the quiz, I said, this is an 8.1 question. So you kind of knew, oh, this is in the substitution section. But on the test, I'll probably say something like use substitution to solve, and I'll give you a hint. Or I might say use trig substitution to solve, or something of that nature. Or for question 3, I might say use integration by parts to solve, because it says x times the cosine of 2x. And so something like that sort of just gives you a hint, helps narrow it down a little bit. Actually, I mean, looking at that quiz, I thought, I don't know how much you had to sort of kill yourself to figure it out, but I really thought people did really well. Obviously, as I said, question 8 was extra credit, and it was kind of brutal. The other thing that's a little bit confusing about this, let me just pick one of these as an example. Like question 9, for instance, you end up drawing a right triangle of that question, and you end up, if you successfully transform it, you transform it into the integral of secant. And so that's the part of this that's a little bit weird. And the reason that is because, well, what's the integral of secant? Well, that was something I showed you in class that was just a breathtakingly brilliant substitution someone came up with. So, on the test, do we always have to rebuild things? In other words, on the quiz, I really did not mean for you to have to rebuild the integral of secant. That substitution you made got it to the integral of secant, and then it's like, oh, okay, we already did that one. In a sense, that's kind of the table idea. In other words, hey, we made that once, we don't have to make it again. I would not want you to have to take the integral of secant on the test and actually have to figure it out, because that's just memorization, because we made a substitution in there. And when you got to that, I hope you either said, well, I don't know, probably because it was a quiz, you thought, well, I got to at least show that I know how to do that. But I hope you went back and looked at my whatever day we talked about that and just kind of stole my logic on that, which I also stole from somebody else. Again, it was a brilliant substitution. So that's kind of a hard part of this. So what I'm going to try to do, because I will definitely put a trig substitution question on there, is make it so that once you make the trig substitution, you get something that's a lot more, oh, okay, I'm home free. Like, I don't want you to end up with the integral of secant. What would be really cool is if you ended up with the integral of cosine or something like that. It's like, oh, okay, I'm done. The integral of cosine is sine. Like, it's super easy. Something of that nature. If you don't, I mean, for instance, on that question, if I actually gave that exact question on the test, I would make sure to solve it ahead of time and then say something on there like as a hint that after you do your initial substitution, you're free to use the table from there, or something of that nature. Um, from your perspective as a student, feeling like, wow, this is a lot, it's overwhelming. We definitely are in the hardest part of this whole class right now. Does that feel right? Like, do you feel like, oh, okay, I could do that on the relative to the amount of time we're putting into this? That's something I could do on the test with those kind of hints mixed in there, and a little bit of you know direction as to when you can kind of punt and use the table and so forth. Does that feel fair to you? Does it feel like, yeah, I can do that then? Any comments on that?
I mean, I don't see why it wouldn't be fair, you know, especially if you're giving us hints.
Yeah.
Yeah, I agree. Giving us hints on a test, that seems super fair in terms of what we're doing and the amount of time we've spent doing it.
Yeah. The other thing is I'm putting a time limit on this because I don't want you to, wander around forever. But in the event that you sort of, kind of ran out of time and you didn't get to the last question or something, I would still rather you just kind of scan what you have, turn it in on time, and then just keep on working on some other piece of paper and then email it to me and, just tell me what happened. Like, I would far rather at least see your answer, even if it took a little bit longer. And especially if you said something in your email like, oh man, question 7 cost me 15 minutes because I did this stupid thing, or I floundered around trying this and it didn't work, and it cost me a bunch of time. Just let me know. I mean, that should happen. Do you see what I'm saying? Like, this is not automatic. I mean, in this class, if there's one thing I've tried to teach you this year, it's like to think, to trust yourself to think and try stuff. Well, that takes time. So, we haven't tried to burn through things and go as fast as we can and memorize all these little tricks and techniques. And it's like, because the real issue here is learning to think, not to get these, irrelevant integral problems right. So that should cost you, right? On at least one question, something should kind of go sideways, and, waste some of your time. And so that's important to me. I really like question 10 on there, because I'm asking you to find the equation for the area of an ellipse, or not the equation, but I'm actually asking you to find a specific area for an ellipse. And that's kind of cool, just because ellipses are fairly ubiquitous. They're out there. So, and that's not a formula you have memorized. I mean, you might have the area of a circle formula memorized, but in class, we found the area of a circle because it involved a trig substitution to find the area of a circle. That was fairly recent before that quiz. And, to jump that to an ellipse, that's what's so cool, is if you understand the logic of how to set this up for a circle, then an ellipse is no different. And that's kind of cool to think, hey, based on calculus, I could find this circle and an ellipse kind of exactly the same. And so that's kind of cool. I'm not really concerned about question 8. The problem with question 8 is, the people that kind of waded into it a little bit, the problem is you make a substitution on it and you end up with the integral of secant cubed minus secant. It's like, gosh, that is possible to do. But again, as an example, since it's integral of secant cubed minus secant, well, the integral of secant, hey, we did that earlier. The integral of secant cubed is, well, it's messy. It's like you're not out of the woods. And that's why I thought, man, that just seems ridiculous. So on the table, we have, one of the things we have is reduction formulas. Like, how do you get secant cubed reduced down to secant of some lower value? Or, you try, maybe I'll replace 1 secant squared of the secant cube. Maybe I'd replace that with tangent squared plus 1, and maybe, maybe that would go somewhere. But it's like, man, that's really ugly. Some of you waded in and made some good progress on that, and I gave you some points for wading into it. Some of you even got the ridiculous question even right, which is super awesome. But again, it's a question of, do I have to get this right entirely with my own, under my own power, or am I allowed to use some of the things we've built in the table and so forth? When I solved that, I used one of the reduction formulas that reduce secant cube down to something else. And which I think is fair. Um, So I think let's do this. Like after class today, if you want to see anything on the quiz just for your own satisfaction, can we do number such and such or whatever? Let's do it. But for now, let's wade into Mr. Simpson. And I'm suddenly reminded that April sent me a cool extra credit. I asked you guys yesterday something I didn't know the answer to, which is, what's the history of Simpson's rule? And, who invented it? Why did it get the name Simpson? I mean, those are just interesting questions. And I'm going to pull that up really quick.
Yeah, I looked that up yesterday when you were saying something about it, but I never said anything about it.
What did you learn?
I learned it was originally created by somebody that wasn't Simpson by looking at wine barrels, but then Simpson refined it later, and it was in the 1600s, 1700s.
Yeah, that's what April found too. That it was. Let's see, who was that? I'm pulling it up, but unfortunately, it takes me forever to log into my own computer now because of this recent software problems. But it had to do with a mathematician who had odd shaped wine barrels, and they were trying to figure out, how much wine was in there. This is what April found, and so how do I find the volume of that shape? Because you've seen a wine barrel, in a sense that the sides of it come down and they're sort of curved, but they're not really a circle. But then the top is flat, and so it's kind of like a football with the top and the bottom chopped off. I mean, it's kind of what a wine barrel looks like, and so you can imagine somebody standing there, wondering. And this was Kepler. I'm looking at, I got April's article. She found out Kepler found the barrel using Simpson's rule. So basically took measurements, and Kepler was a astronomer and a mathematician. And it ended up named after a person named Thomas Simpson in the 1700s, taught himself a lot of math. I love that one thing April found is he married a 50-year-old widow when he was 19 years old. He was 19. He married a 50-year-old with 2 kids.
That's hilarious.
But interesting guy. He dabbled in astrology, divination, the latter of which got him kicked out of the town of Derby, and he also taught math for most of his life. Mathematicians are weird. Right there proves it even back in the 1700s. And to that end, I'd like to show you something about that right now. And I kind of hinted at this going out the door yesterday. But what's powerful about Simpson's rules is you just need to take your own measurements. And so I'll just make something up to make this kind of quick. And you have a problem like this in your assignment, so I think it's kind of cool. And then you have to decide, do you want me to show you where Simpson's rule came from? Because I liked Eve's comment yesterday. It's like, what is this? I don't remember how you worded it, Eve, but it was something like, this is ridiculous. This is like magic. How can this possibly work? Just multiplying by 4s and 2s, and suddenly we get this ridiculously accurate answer. It's just ingenious what people dream up. So let's take a little further look at Mr. Simpson. So the gist of it, and you can think about this with respect to the wine barrel. Well, let's even make up a question like the wine barrel. Why not? What the hey? What the hey? Something like that. And you can appreciate a wine barrel, at least in theory, would be really symmetrical, but maybe in practice not. I know what they're really doing is just cutting boards and kind of sitting them inside of bands. I mean, I think it's a pretty fascinating thing. I saw some little piece on it once on some kind of a show. But to keep it simple, we won't even do this as a volume problem. Why not? Let's do it as a volume problem. Let's make it more interesting. Bam, just turned into a volume. So How would you apply Simpson's rule to something like this? And I'm going to purposely kind of pretend it's a little a little asymmetrical just to make it more interesting, and because my drawing is not very good. So does it make sense you'd have to divide this into even parts? And so I'm going to divide this into even parts, except I'm going to do it kind of in sort of a wimpy way. So there we go. There's four rectangles, except for, notice in this case, they're not even rectangles. So 4 rectangles, which is going to take 5 measurements. Does that make sense to you? So we're picking n equals 4, which is a little on the lazy side. And that's fine. Matter of fact, it feels lazy enough that I suddenly think, let's do 6. We can handle that. So it's going to take us 7 measurements. What's it going to take to find a volume? How are we going to do? How are we going to use this to find a volume, not just an area? Well, it's kind of like calculus in the sense that you got to think of that as like a slice. In other words, we're taking I guess you could say, almost like what we did with calculus earlier when we found volumes of things that were rotated. In other words, aren't those just a bunch of disks? In other words, the thing that's amazing about Simpson's rule is you can actually just add anything together. And so does it make sense I could take a measurement here? So again, I'm just going to make these up. So I'm going to say, I don't know, how big is a barrel? We're going to say 8, we'll make it easy and say 18 inches. So if this is kind of number 1, number 2, etc., all the way to 7, since there's 6 of them, does it make sense I guess the other thing I would have to measure is how far apart are each of these? Again, let's think about a barrel here for a minute. I'm going with, I don't know, 4 feet, which is 48 inches, divided by 6 would be 8 inches. So does it make sense if I measured this and it was 48 inches long and I'd broke it into 6 parts evenly? 48 divided by 6 would be 8. So isn't 8 my change of x, if you will? So what do you think? I'm making this up, so I'm actually not even sure what I think the answer to this question is. So since we know the volume of that cylinder is pi times radius squared times h, I know for number 1 that would be pi times, well, if the diameter was 9, then wouldn't the radius, I'm sorry, the diameter was 18, then wouldn't the radius be 9? And now here's where I'm a little stuck. Like, you help me figure this out because I've never tried this before. What are we going to call the height of that? How tall should we make that?
The problem with our height is it's constantly changing. That's why we had the dx in calculus used as our height. But in this case, because it's actual lengths and it's constantly changing, you run into a pickle.
Yeah, do you see what I'm getting at? In other words, we can't just say this is dx down here and make it teeny, because then we're going to be adding 7 teeny cylinders together, and that's not going to be the volume. So I don't think I want the height to be dx, or something tiny. It's not going to be like 1 inch or something.
Wait, is your height your Simpson rule? Because it's the lengths of your rectangles.
Lengths of my rectangles. Well, like in a normal graph, our height, I mean, the cool thing about Simpson's rule is you can sort of add up anything. So if we were doing this with area, and maybe I'll back off and do an easier question in a second, but my gut reaction is to think that, if I think of this as my, the size of, I guess, cylinder number 6, it sort of feels like it should be this, doesn't it? Do you agree with this?
You're pretty much using the midpoint for the ring num sum.
Yeah. I mean, isn't it like, this makes me want to say, I think we should use the height of 8, shouldn't we? Because wouldn't that wouldn't that kind of fill the barrel up with cylinders? I mean, the cylinders all have to be touching each other, don't they? You agree with that? You think the height is 8? That's kind of what I'm thinking. Again, I'm making this up, so we're all thinking together here. So I think it's the change of X in this case. So basically what I'm adding is all my cylinders are 8 inches tall. And that makes sense to me until you get to the end. Do you agree with that? Here's the part that I'm kind of struggling with. When I get to the end right here, then aren't I kind of adding, I'm adding a whole bottom down here that's not really there. I'm like half of it's not there. You see what I'm saying? So wouldn't I be adding too much if I did that? And maybe this is what Caesar was getting at. Should I be?
Well, I guess what you could possibly do is, since you're adding like an extra, you're adding basically twice as much as you normally would, just don't do it on the other end.
Yeah, leave one of them out. Is that what you're saying?
Yeah.
I like that idea. Except for then I'm going to end up with 6 of them. I'm going to end up with 6 cylinders if I do that. And remember our little formula that goes 1 and then 4 and then 2 4 2 4 2 4 2 4. And then it's really important it ends with 4 1 again. And so with n equals 6, then I'm going to have 7 numbers, and I need 7 numbers in order for that pattern to work. So if I only have 6 cylinders to add, that's going to kind of screw that up. In the same respect, what I think, similar idea that I think Caesar was getting at is if this was my, if these were my cylinders, then why wouldn't I just make it, like right, oops, that's not the right direction. Why wouldn't I just make it right there? In other words, this is my first cylinder. Does that make sense? And again, I think it was Caesar that said this. Then I could use the midpoint for that. So does it make sense that choosing, we need an odd number, even though n is 6, we need an odd number of actual cylinders to get this to work. Do you understand what I mean by that? So, okay, I think I have an idea now. Again, I just think this is fun. Like let's try to figure it out for ourselves. So let's see, I'm gonna do this terribly. But to make it go a little bit faster, I'm gonna try to divide this into 5. That's not bad. There we go. Let's try this and just see what we get. So the key to choosing 6 rectangles is because that actually gives us 7 numbers to add up. Does that make sense? So I'm wondering in this barrel example that maybe I actually need 5. In a sense, I'm gonna have 5 numbers here. And so the height or change of X for all of these, notice if I do 5 of them, 48 divided by 5 is no longer the nice answer I had before. What is that, 9.6, I think? Don't want to get it wrong. 48 divided by 5, yeah, it's 9.6. So my change of X here is 9.6. So then I'm just looking at each of these cylinders right here. So I know its height is 9.6, so that change of X will be equal to the height. And then as a radius, does it make sense I could actually take these measurements kind of just to get it accurate? I think this is what Caesar was saying. So this is kind of number 1. So let's say in your assignment kind of looks like this. Let's say number 1 has a diameter we'll just go back to what I had before, like 18, and then number 2 up here would have a diameter that's a little bigger than that. Let's give it a diameter of 20. Let's keep it kind of easy. Say in the middle, it made it up to 23 because it wasn't symmetrical. And then going back down the other side, you'd think it would be symmetrical, but let's just say it, you know, it didn't work out that way. And we'll even make it a little bit, I mean, it doesn't have to be whole numbers, I guess. And maybe when it got to the bottom, it was actually 19. So those are all of its diameters. So then its areas, I should say volume, I guess. Since it's pi times radius squared times height, and remember that is basically our height, our change of x in this case would be the height of our cylinder. So if I take pi times the radius of 18, which is 9, squared times 9.6, I get a volume of, I'll just round it off, 2443. I got 2442.9. And when I do that with 20, which would be the same exact problem, except for it'd be 10 squared, I get 3016. When I do it with 23, which would be 11.5, I get rounded off again, 303989. And when I do it with 10.5, half of 21, I get 332, I'm sorry, 3325. That's a 3. And lastly, with 19, which would be 9.5, delete 9.5, I get a volume of 2722. I don't know, is this working? What do you think? Now I'm suddenly thinking, isn't this more like a Riemann sum? Like, why don't I just add those up and I'm done? Like, that's a decent answer right there. I'm suddenly thinking if I start multiplying this by 4s and 2s, I'm going to get a gigantic answer that doesn't make any sense at all. I'm thinking I maybe wandered. Should have stuck to something I'd already thought about before class. I think I'll go ahead and continue this really quickly, but then I'm gonna leave it to you to kind of figure this out as extra credit so we don't waste too much time. If I just actually added those together really quickly, 2443 plus 3016 plus 3989 plus 3325 plus 2722, I get like 15,495 cubic inches. All of our measurements were in inches. So if I tried to do Simpson's rule, we'd say Simpson's rule said you take the change of x, divide by 3, and then you take the first number plus 4 times the next number. Doesn't it seem like it's going to be way too big? Plus 2 times the next number, plus 4 times the next number, plus the last number. Do you see why in this case I needed 5 of them? Because I actually have to have an odd number of numbers in order for that pattern to work. Notice it went 1 and then 4 and then 2 and then it ended 4 1. It's symmetrical. 1 4 2 4 1. It's symmetrical. So I needed 5 numbers to do that. But isn't that going to be huge? Yeah, that's going to be huge. That's not right. So how does Simpson's rule work in this case? I love to think. I love to try to figure stuff out. Thinking is fun. In this case, I'm adding volumes, and so I had to have something of a volume, but let's back off and do an easier question just for a second. And maybe this will help us think about it. And your question and your assignment is a little bit more like this anyway. And maybe this will give us some help. And so similarly, let's do the same. Let's do kind of the same question, but let's just pretend it was a yard like I showed you yesterday. And let's make it kind of, I'll make it easy by kind of having the ends chopped off for you, but so you have this weird shape and you want to know the area of it. And so you have to divide this into an even number of spaces so that you end up with an odd number of numbers to add together. So let's go back to what we did a second ago. I'm going to divide it into 6 parts so that I end up with 7 numbers to add together. And so this is more of a classic Simpson's rule problem that I sort of know I understand. I think converting that to volume was a little bit weird. And so let me just throw some measurements on this, and I won't even take the time to do a good job with this, but let's say this is like 8 feet. I'll make them whole numbers just to make it nice and easy for us, even though if you measured them yourself, they wouldn't be this. And does it make sense? You could like go out in the grass and get a tape measure out and actually lay this out. What would be important is that every one of these changes of X here is identical. Notice mine isn't drawn very good because this is way bigger than that is. And so my drawing's kind of terrible. Like you'd have to choose a measurement and cut this evenly into 6 parts like I did, or 8 parts or 20 parts. So let's say our change of X is, we chose 6 feet for that. And I'm just going to come in here and give you sizes for these. This is 10 feet. This is 11 feet. This grew quite a bit. We'll say that's 13 feet. This grew a little more. We'll say it's 15 feet. This grew a little more still. This is 16 feet. And then this went back down to 12 feet. And Simpson's rule is saying, hey, those are the Y values. Those are the heights. And so this is going to turn heights into areas. And this is what's wrong back here somehow. Like I had volumes, and the volumes I added up as volumes. Well, down here, these are just heights, and yet this is going to produce area. Does that make sense? It's like a whole dimension behind, and I suddenly have an idea about how the barrel would work, but let's go back to that in a minute. So Simpson's rule says if you take the change of X, which is 6, in other words, how far apart, how much distance is there between each of these, and you divide by 3 every time, and you simply add those numbers together, except multiplying them by 1s and 4s. And so I'll go ahead and write the 1 in this time. 1 times 8 plus 4 times 10 plus 2 times 11 plus 4 times 13 plus 2 times 15 plus 4 times 16. Notice the pattern worked. Plus 1 times 12. It worked. It's symmetrical. It started with 1, 4, 2 and then ended with 2, 4, 1. Doesn't matter how much stuff is in between. And so notice I'm actually turning lengths into areas. Does that make sense? I'm adding lengths and yet that's turning into an area. That was what was wrong with the barrels. I took volumes and turned them into volumes. I'm wondering if I could have done areas of circles and turned them into volumes. I think that's what's wrong with the barrel. I think I figured it out. So let's see, this is 2 times 8 plus, why am I doing this? Just write it out. 8 plus 40 plus 22 plus 40 and 12 is 52 plus 30 plus 64 plus 12. If I just simply add all that up and multiply by 2, that's a ridiculously good answer we learned yesterday for the area of that weird yard. You're never going to find a formula that models the sides of that yard. And so this is just remarkable that works. And we don't really have any way to check this, but so 40 plus 8 plus 22 plus 52, making sure I'm typing all this in right, plus 94 plus 12, got 228 multiplied by 2, I got 456. So 456 square feet, since all of these is a great estimate for its area. That's cool. That's calculus. But notice all you're doing is adding and multiplying to come up with an answer for that. It'd be neat if there was some way to know the correct answer for this to kind of see how close it really was. But notice that's not hard math. Like in my own house, I have these weird yards, and I hired somebody to come out here and spray grass seed on it. You know, it costs like $600 or something, and spray it out there. And it made me wonder when the person came out, like, what do they do to come up with the area? Because they sort of charge it for the area that they're spraying, but it just made me wonder, how do they do that? They probably just, you know, rectangles, and you know, I'm sure they don't do this, but it'd be kind of cool if they did. But notice it's actually not that hard. You don't have to know calculus to use Simpson's rule. If you can add and multiply, you can use Simpson's rule. So do you agree we added a one-dimensional length and it produced a two-dimensional area? So here's my idea with the barrel, and I'll let you follow this up. If you want to, just out of curiosity. So would you agree this is actually a pretty decent estimate based on just Riemann sums? Like I don't know if I spelled Riemann right. That's a pretty decent estimate based on Riemann sums, but here's my idea. So this is not going to work. That's going to be gigantic and not even close to the right answer. But I'm wondering, is it dimensional? In other words, we're trying to get a volume. So would it make sense to add up areas? I'm actually back to this original picture now, thinking here's my idea. You're not even adding up cylinders, you're adding up circles. You see what I'm saying? If we added up the area of these 7 circles right here, I'm thinking that would produce it. I'm thinking that's the right answer now. If we add up 7 circles, then that would actually give us a volume. I mean, that's the beauty of Simpson's rule. It's actually taking lengths and turning it into an area, 1 dimension turning it into 2. So here I'm thinking maybe it takes 2 dimensions and turns it into 3. So if I found the area of those in my original blue barrel anyway, the area of those 7 circles, then I think that would actually produce the volume of the barrel. That's what I'm thinking. But notice in that case, it'd be back to 7, like this down here with 5. This was a good Riemann sum estimate. But I'm thinking Simpson's rule would do it even better. I mean, I think that's the idea here. Anyway, I'll leave you to think about that. So I want this to be like a super easy test question for you, as long as you have the formula in front of you, and you will. Let me look really quick. Do I already have that on the calculus final exam notes? No, that's for Math 112. I don't know if I have this in here. Quick look to see if I do, but I would have it in the notes for you. So final exam notes. No, I don't have it. Maybe I'll show it to you before class is over. But as long as you had Simpson's rule in front of you, like this is easy point. So let's just do one more quick question. And all I'm going to do is just tell you the answer. I'm going to work on it on the side just like you are. But if I just made up a weird example and said, let's see, I got to make sure it's going to work. So I'm going to say natural log of the sine of x which of course feels like, man, please don't make me take the integral of that, right? Doesn't it feel like that's not good? I don't want the integral of that. Y equals, let's make sure the natural log of, bam, the sine of x, bam. So what does that graph look like? Whoa. We had this zoom square. Whoa. That's a terrifying example. I don't think I like it. I'm afraid that it's got asymptotes in it, and it's got places where you can't take the natural log. So I'm thinking, do something trigonometric maybe. Or maybe, what about e? What about e raised to the sine of x power? Let's try that. That seems terrifying to try to find the integral of, does it not? There we go. That's beautiful. So it's a continuous graph. I think it's awesome. And let's find the area of e to the sine of x. Ooh, man, I really don't want to take the integral of that. And let's do it between, I don't know, 1 and 5. Let's say. So I have to look at the graph to make sure it exists. And again, for you future math teachers, it's part of the reason I'm making this stuff up on the fly. It's not because I'm lazy and can't do it before class starts. It's because I want you to learn how to think and like play around. It's like, that's the whole fun of it. It's why I tried the barrel thing, even though I didn't, it just occurred to me while we're sitting here talking. It's like, we're having a conversation. This isn't a monologue. So I looked at the graph and I see the graph exists. There was no holes in it. I'm kind of glad the natural log of sine wasn't real nice. So can you use Simpson's rule? What decisions do we have to make? What else do I have to tell you on a test if I want it to, be able to grade this and get the right answer?
Wouldn't we need the number of divisions?
That's exactly right. I got to tell you how many rectangles to use, right? And I'm not going to say something like 20 because then you're going to be there forever. I want to say something smallish. Let's say 6. That seems reasonable. 6 rectangles, which is going to create 7 numbers. And of course, check this in Desmos or whatever. Like you should not get this wrong and not know it. If you might punch a button wrong or write something down wrong. So the only difference in this and the grass problem is just you're getting your heights from this equation. This equation is telling you what your heights are, whereas from the grass, we had to bust out a tape measure.
Seems like this is a little easier because you got an equation to plug it into.
That's exactly right, Justin. This is actually easier, but irrelevant, right? Like why would you ever use Simpson's rule for this when you have software, but you can appreciate people that didn't have graphing calculators. Remember, this was invented in the 1700s. We've only had graphing calculators for like 40 years. So nobody could ever answer these questions. The internet was only 1990. So, we're kind of spoiled. Like, don't forget, you're not the only people that ever lived, but it's like for hundreds of years, people could only get the answer to this question because maybe it's not solvable.
Yeah, I feel like being a mathematician back then was probably a lot more impressive.
Yeah, true. Again, I struggle with that. Calculus seems like it's a little irrelevant. Can you go to the table and produce all these values? Like, go to the table in your calculator to get all your values. So I'm going into y equals, typing e raised to the sine of x. Man, that's a beautiful graph. You've got their mic on with noise in the background. Somebody. So I'm going to table set. I'm saying we're starting at 1. Everybody figure out what the change of x is? And for any of you who have any computer related skills, the idea that I have to take these 7 numbers and write them all down and add them all up by hand when some kind of an iterative routine would do it for me. I could get a machine to do this like that. That's bothering you if you're a computer minded person. I'm not really, but I've programmed enough in even the TI that, you know, making the Riemann sum program and so forth, that it bothers me because like I'm going to write them down like an idiot and then probably not copy them right. Remember, I made 2 mistakes doing this yesterday.
It would probably take me longer to just write a simple for loop without having any errors or problems than it would to write down the numbers and add them up.
That's right, too.
Once I sat down to try and do it, I would encounter a lot of trouble for a simple task.
Very true. And all I have to do is add the number 0 to this problem and make the 6 60, and then all of a sudden it is worth your time, right?
Yeah, I was going to say if that number was a little larger, then it would be totally worth the time, because a for loop takes a couple seconds to write. But the thing is, incorporating that E in there would be really weird.
Yeah.
Do we know for sure, like obviously on a test you would want us to use Simpson rule, but do we know for sure that this this equation isn't solvable through integral calculus, like substitution or some way? But I feel like you could like substitute sine of x for u and then solve e to the u.
Yeah, that's a wonderful question, Eve, and that's part of the reason again why I made this up on the fly, because I don't know the answer to that. And again, I hope all of you are curious enough that you either, you know, wish you had more time and would try to tackle it, or perhaps you do have more time and after class would like to go, you know, down the rabbit hole of, is there some way I could just solve that accurately, you know, get it perfectly right? And you should agree from what what we've learned in this class, that if you could pull that off, that'd be kind of cool, wouldn't it? You can say all you losers adding up your 4s and 2s and so forth, and you don't even get the right answer. And I'm over here with my big math brain and I figured out a way to get it perfect. You know, it's kind of cool. There's something cool about that. Again, that's the difference between a mathematician and an engineer's mindset. So yeah, I'm definitely not sure, Eve. I'm a little worried about letting u be sine of x, because when you take its derivative, you're going to get the cosine of x. And so, yeah, that turns into e to the u, but then there's going to be a cosine there, right? And so, you know, will I be able to get rid of that? It's not going to be just as easy as it suddenly turned into e to the u. So I love how you're thinking, Eve. Out of laziness, I'm going to round this off to 2 decimal places. Did you get this? Let's see, I'm going to have 7 of these numbers. 1, 2, 3, 4, 5, 6. It's hard to tell on your calculator whether you're getting them right, whether you have enough of them. But I do notice when I get to the last one, hey, I'm at x is 5. So don't trust myself, so I'm going to re-stare at what I'm looking at my table, re-staring at what I just typed there to make sure that I agree with what I typed in, just to see if I could even read it out of the table right. I'm seeing miracles. Is that what you had? This is another place your graphing calculator is so wonderful, because you should, as you're typing all of this in, I'm literally typing what I have sitting there in red. I can either just go really slow, but I can also look back. And remember, I would go to Desmos to get the right answer to this and expect it to be really close. And so if it wasn't, then I would at least know to go back to my graphing calculator and, you know, open this list back up again and see if I didn't blow it somewhere. For myself personally, if I don't get this wrong, I'm actually really surprised that I typed every single number in right. In my case, because I'm sitting here babbling while I'm trying to answer the question. I got 50, which seems way too big. So I'm almost thinking for sure I'm wrong again. So I'm re-looking at what I typed. All you got to do is be missing a plus sign, so that's this giant multiplication problem because you forgot a plus sign somewhere and it wouldn't work. So I'm ready to say the answer is 50.08, but I'm like almost sure that's wrong. Just looking at the graph a second ago quickly, it's like that area into that wasn't 50. Going into Desmos, see what the right answer is to check my work. And I'm hoping I got this wrong. Just because again, I'm trying to illustrate to you how to do math. Yep, I got it wrong. So it should be 5.55. So my instinct was right. Fortunately, my answer was so wrong that it didn't look right on the graph. So I now know the right answer, which is why computers are so cool. And now I know if I'm you and I'm sitting there on the test that, well, something's wrong here. So I'm rechecking my graph. This is what you should be doing. I'm rechecking my graph. I'm rechecking my table. Did I really get this right? 2.32, 2.7, 2.06, 1.15, 0.61,
Hey, Doug.
1.38.
I have a question about the table set actually. Would I change my change of table to 2 or would I leave it at 1?
Yeah, what's the change of your table? Well, remember it's the change of X is how much room do you have to work? I'm going from 5 to 1, so I'm going a distance of 4, but then I decided to break it into 6 rectangles, and so I get 4, 6, or 2/3. So that's your change of X, 2/3. Oh, that's what's wrong. That's what's wrong. I put a 6 there. What goes there? Change of X. It's 2/3. Again, I wish I could say I did that on purpose. I wish I could say I did that on purpose for your knowledge, but again, isn't that kind of an understandable mistake? It's like I got excited and put a 6 there. It's really 2/3. So maybe I didn't type anything in wrong. Again, I love the graphing calculator because I have that whole mess typed in. So all I have to do is recreate it, go back to the start and say 2/3 divided by 3, which is really 2/9. And when I say 2/9, bam, I get the right answer. Oh, whew. Again, but like, what, didn't that just cost me 10 more minutes because I'm dumb? Cost me 10 minutes and, now I didn't get my test done. It's not like this is hard, but there's just all kinds of dumb mistakes you can make. I'm amazed at how many dumb mistakes I make. It's embarrassing. And notice my calculator actually says 44444, which goes forever, which means I actually could turn that into a fraction. But remember, this is an approximation anyway, so that's kind of dumb to do that because I rounded all these numbers off to 2 decimal places. So I think to say the area is approximately 5.56 makes a lot more sense. Like, that's what I'm going to stick on the test. Just a question like that. And I would say use Simpson's rule, because if I didn't say that, then you could sit there for 2 hours trying to solve an integral that was not possible. And on top of it, I'm probably going to come up with something like this that's weird so that you can't take it any other way. Does that make sense? Like, I don't want you to do it. But to yesterday's point, are you not, my friends, staggered by the ridiculous level of accuracy that this seems to produce? I mean, I hope you're just blown out by that. If you're not, you're missing one of the beauties of all of math. I mean, I got 5.564 for my answer when I added all those up. And notice I was actually pretty lazy in the sense that I chose to round these to 2 decimal places. That was kind of lazy on my part. I mean, if I'd have carried those out to a couple more decimal places, it probably would have even been better. But notice rounded to 2 decimal places, I actually got it exactly right. Like the answer the calculator gave would have been 5.56 if I rounded to 2 decimal places. And so it's actually accurate to the 100th place. And I literally added up 6 rectangles to do it. I mean, this is just mind boggling. You got a chill on you? You got a chill going down your spine right now? Whoa, this is rad. I can't believe this works. Hmm. Trying to decide if I'm going to say something to you about error. In the interest of time, I don't think I want to. I don't want to burn this whole period because we've almost burned it all anyway. The last 2 questions on your 8.8 assignment talk about error, and that's really cool. And they say, you know, like, again, pretend we didn't have the ability to cheat here. Like we got 5.56, and if that's all we had, we'd be wondering, I wonder how far that's off. I wonder how reliable that is. I wonder if that's, you know, I wonder if that's good enough. Because remember, if it's not, you can always say, well, let's do this with 8 rectangles or 12 rectangles. If you throw in a few more rectangles, by the way, I won't explain why, but if you doubled the number of rectangles from 6 to 12, you just made the answer 16 times more accurate using Simpson's rule. 16 times more accurate. Wow. By doubling, you don't get the answer double accurate, you get it 16 times more accurate. So spending time, you can understand, without, we don't really need error so much because we have a cheat button, if you will, to come up with the error. So let's omit those last 2 questions because I don't want to spend 20 minutes explaining the formula as to why that works, why it works. And it's really kind of brilliant, but it's in your book. If you want to look at it, you can. I guess I'll just leave them in there. I'll leave them in there for extra credit if you want to figure out the rule as to how the error works. I mean, it's a kind of a hard read, and it talks about taking the 4th derivative of this expression and figuring out what the maximum value for that is and so forth. It's kind of neat. But we're winding down this class, and the last thing I want to do is just jam all this stuff on you and leave you feeling all confused. So go into the chat right now. Do you want to know where Simpson's rule comes? You've got 2 choices now. I could spend the last 20 minutes showing you where Simpson's rule comes from, and then we'll do the project tomorrow. Or I could introduce the project to you now so that you get a head start on it, and then have now plus tomorrow to work on that project and get it done. They're obviously both good. I'm not opposed to actually starting the project now, and then for those that want to stay after class, and I can show you where Simpson's rule comes from. What's your thoughts? I guess say it out loud. I was going to say go to the chat, but say it out loud. What do you think? What do you want to do with this last 20-30 minutes? Not
I think
everybody's going to be the same, so
uh,
go ahead, Jaleesa.
yeah, sorry. I think I would choose to do the project, like a head start over it.
Yeah. And somebody else?
I agree with starting the project.
Mm-hmm.
I'm on board for the project too.
Okay, let's do it. That makes more sense because, you know, you want to get this class over with. If you want to stay after, then we'll do it. Maybe none of you care where Simpson's rule comes from, and that's perfectly fine too. So I posted the project, and it's kind of a cool one. The downside of it is it takes Excel to do this project, and I would have you in a lab, and so I'm hoping that you have access to a spreadsheet program. It doesn't actually have to be Excel. But we're going to actually use Simpson's rule to do something rather cool. So let me give you a brief explanation of that, and this is what will give you head start on this. So who knows what the and maybe some of you took statistics, but who knows what the normal distribution or the bell-shaped curve is all about, either because of some reading you've done or from a statistics class. And by the way, go to my open math right now and pull the project up so that you're looking at that too. But does anybody want to take a stab at just kind of a off the cuff explanation of what the bell curve is? What does that do? The normal distribution, the normal curve, or the bell curve, it's sometimes called, it kind of has this look to it.
Doesn't it just display like the majority of results that are in the top of the bell curve is like the most common, and then you'll have percentiles of not error, but a deviation, I guess, is the best from the normal, which is the top of the bell curve.
Yeah, that's exactly right. So let's pick something like a baby. Babies are born, and some of you maybe have kids already, and others of you may have them down the road. But one of the things you find yourself concerned about when you have a child is, oh my gosh, are they okay? I mean, is everything good? And so I'm going to make this up because I don't know the answer, but let's say the average weight. Let's talk about the weight of a child. Let's say the average weight is, I don't know, what do you think it is? 22 ounces? I can't remember. My kids are 30 now. So I'm going to say the average weight is 22 ounces of a child is born. And so, if your kid's not 22 ounces, it's like, oh no, my kid's 20. Like, does that stress you out? Oh no, my kid's going to die. They're starving to death. They're only 20 ounces or whatever. The bell curve is the fact that, well, that's the average, but no one is the average, right? You're either a little above or a little below. And it turns out that if this is the average, sometimes that's given as X bar, there's a thing called the standard deviation. And the standard deviation, we'll say, just to keep it simple, we'll say is 3 ounces. And so what that means is, yeah, the average is 22 ounces, but it's not weird. In other words, it's actually typical to deviate from that by 3. In other words, that would be very, very comforting to you if your kid was 20 ounces, because the doctor said, hey, it's actually typical for people to vary from that by 3. So in other words, oh, okay, so that means if my kid was anywhere from 19 to, and that's 22 minus 3, to 22 plus 3, which is 25, that would be incredibly typical. Does that make sense? And so it's like, whew, okay, great. So that's one standard deviation, one typical deviation away from the mean. It turns out, and I think I said this on my sheet, that actually encompasses 68% of the kids born. That 68% is what we're going to talk about today. 68% of kids born would be inside that range right there. Now, let me show you something really cool. So it turns out the equation for this curve, which I doubt any of you have ever seen before, I don't have it memorized, so I'm looking over at it right now. The equation for that curve is 1 over 2 pi square rooted. You might go into Desmos. I'm going to go to Desmos and graph this in a second, but you can do it too. Times e raised to the, oh no, I forgot the formula. I don't have it in front of me. X minus the mean. Negative x minus the mean, which for us is 22 squared. Oh man, do I have this written down somewhere? Hey Siri, what's the formula for the normal distribution curve?
Here's what I found.
Who do let's go with math is fun, because that's true, math is fun. I'm showing you a slightly more complicated version of this formula than what's sitting on your sitting on your formula sheet, just because I'm trying to help you understand this a little better. That didn't work. Hey Siri, what's the formula for standard deviation? I'm sorry, that's not true. Hey Siri, what's the formula for the normal distribution?
I found this on the web.
Let's try Wikipedia. There it is. That's what I couldn't remember. So we'll talk about this in a little bit, but that's x minus the mean. That mu symbol is the 22, and that sigma on the bottom is our 3, and that's what I couldn't remember for sure was, where did that go? So now we got it. So it's x divided by 3. Now what that's going to give you is our curve that's centered on 22, and you should know some algebra, and part of me says I should have figured that part out, which is x minus 22. Doesn't that slide the normal distribution right 22? So that's going to put our normal distribution right on 22. I just couldn't remember about the sigma, the standard deviation, where that went. And then there was also a 1/2 out in front of this. So it was actually negative 1/2. So there's the formula. So let's go graph this. This is kind of cool. So y equals 1 divided by the square root of 2 times pi. Where's pi? Can I write pi? Where's pi on this thing? Pi, that's right. And then we're raising e to a complicated exponent. Wow, what an amazing formula this is. E is raised to the negative 0.5 times x minus 22 close the parenthesis divided by 3. Yeah, that's okay, except for I need a second. 0.5 is not inside that parenthesis, so we need a second parenthesis. Divided by 3. Get rid of that one. Close the parenthesis. Squared. I think that's it. Yeah, I think that's it. Notice, hey, look, bell-shaped curve. Now, what I'm going to do is just change the size of the window a little bit to make it look a little nicer. So I'm going to say, let's have the y value be from 0 to 1. Bam, right there at 22. Notice that looks like a bell-shaped curve. And so here's what's really cool about this. Watch this. Let's cheat and use Desmos for a second here to do some of our thinking for us. So if I said, and this is what you do in a statistics class, and this is where I got 68% a minute ago. If you say, I would like to know the area under that curve, we're cheating to find the area under that curve. And we said, since the standard deviation was 3, 22 minus 3 was 19. 22 plus 3 was 25. And I said, I'd like to know the area under that curve. Dx, bam.
So we actually have an equation for the normal curve. Oh, that's the first equation is okay.
Now let's see what's wrong with this. 19 to 25. Da, da. That is not true. What is wrong with this? negative x minus 22 squared over 3 is 3 part of the squared. So let's leave it at this for now. So can you appreciate that the magnitude of this equation? That's going to be a very hard integral to take because it's basically e to the x squared. And so it turns out the area under this would tell you the percentage, and there's something wrong with this. It would tell you the percentage of people that would be in that range. And so what's wrong with this is that number shouldn't be more than 2.
Did you account for the negative x squared over 2? Did you account for the division of 2?
I think so, because I typed negative 1/2 there, and the bell curve looks right. So it was supposed to be negative x squared over 2. So that's negative 1/2 times x squared. And so what I think I just saw, thinking out loud, didn't I type that in right? Oh, look, I see something's missing. What's missing in my formula? There's a little sigma out in front of square root of 2 pi. That's 3. So there's a 3 out there. So I got too much of a hurry. So, bam, 3. There we go. Fixed. So that's still the bell curve, but notice what percentage of kids are between 19 and 25? 68%. That's cool. So that actually means 68% of people are within one typical deviation from that mean. And so that's very powerful. And so if your kid is outside of 19 to 25 when they're born, are you terrified? No, because 68% still leaves 32%. Like a third of people are either a little bigger or a little smaller than that. What if we took it out to 2 standard deviations? 22 plus 2 3s. That'd be 22 plus 6, which would be 28, would it not? And what if we went 22 minus 2 3s? 22 minus 6, wouldn't that take us down to 16? What percent of kids fall between 2 standard deviations of the mean? Well, notice that's up to 95%. Do you see that on the sheet that I produced? Notice how it says 95% are within 2 standard deviations of the mean. Now, as a parent, are you concerned if your kid is outside of that? Yeah, ish. In other words, there's still 5%. 5% is 1 out of 20. So 1 out of 20 kids is going to be either bigger or smaller than this. And so you're concerned. This is where doctors draw the line. They say if you're outside of 2 typical deviations, then we say, oh, that's unusual. Is it terrifying they're going to die? No. If they're on the low side, we'd say, okay, well, let's just, make sure we feed them, make sure feeding is working good, and let's check again in a month and see where they fall relative to other kids after a month old. Or maybe the other way around. Maybe they're on the high side and so forth. So you look into it. Is there any problem? You just kind of, at least that gives you an alarm to check. I mean, do you see how practical this is if you've never taken a stat class? But the problem is do you see how we need the area under the curve? But it's like, well, look at the equation. It's e to the x squared. And so it's kind of like e to the sine. And it turns out that is an integral that you can't take very well. Now, what we're going to do is, and I kind of gave you the sheet. We're going to play around with this, except for we're going to work with a chart that is often given. So let me pull that up. Again, the beautiful thing about what I just showed you, because you guys are a little more advanced mathematically, I just showed you the equation for this. And now you can answer any of those questions entirely just using Desmos. Game over, we're all done. But what lives in a normal calculus or a normal statistics book, the problem is people that take statistics don't need to take calculus. Like, that's a lot to ask. And so they end up with this standard, they end up with this chart in their book, or somebody teaches them how to poke buttons into your graphing calculator. It turns out a bunch of this stuff is in your graphing calculator. And so they have this chart, but the point is this chart actually comes from calculus. And because you can't take the integral, because you can't take the area under that curve easily, enter Simpson's rule. So I want to show you how to kind of make that chart. What we're ultimately going to try to do, this is a typical page out of a stat text. As I said at the top, the goal of this project is to make the portion of this chart over here in red that is in every stat text. And notice what it's telling you is this table is telling you what % of people are between 0 and 1 standard deviation. What % of people are between 0 and 1? Well, remember, between 1 and -1 was 68%. So half of that, half of 68 would be 34. Well, notice what this chart says right there at 1, from 0 to 1, that red area right there, that says 34%. So that's the upper half. If we included the lower half, that'd be 68%. And so this is a really usable chart based on calculus, but you're in a spot where you might be able to understand this. So I want to help you try to create this chart right here in Excel. So let's see if we can make a little bit of sense of this. Now, why is this equation so simple? Well, notice right here, this is really cool. If you make the mean 0, not 19 like we did for the kid, and the standard deviation 1, then what you're actually getting here is a chart that works kind of for everything. So notice our equation got simpler because there was a sigma out in front of this. Well, it's 1 now, so see how it's not there? And then if the mean is 0, notice it's x minus 0, not x minus 19. And then we're dividing by 1, and so see how the formula got simpler? So what you're doing then, and notice I said here, use Simpson's rule and a change of x, thanks to computers, of 0.01. Like, that's a really tiny change of x. Would you agree with that? It's really small to create this table. So what we're going to do then is, well, create this table. And so notice across the top, you're just typing this in 0, 0.01, 0.02, all the way up to 0.1. And so we just need to create the green part of this table right now. Let's see if we can kind of do that together. If you have Excel or some program like Excel, I'm going to pull Excel up right now and start kind of playing with this same concept. And again, I just kind of want to help you do this and try to help you understand. This is just kind of a cool thing to understand in the world. So let's open up an Excel file. Boom. So I'm going to give myself some room. And so I'm saying 0. Let me show you a couple cool tricks here. 0. We said we're going to move to 0.01. And if you grab those two, you can just keep typing 0.02, 0.03, 0.04. But if I grab those two right there, there's a little box down here. I can just drag that to the right, and it kind of reads my mind and says, oh, you apparently are increasing by 0.01. And so it just did that automatically for me. And so I dragged it a little too far, so I don't need this one. And I think that's it. I needed all the rest of them. So yeah, it went from 0 to 0.1. So let's see, I'm going to go, you don't have to do this, but I'm going to go to the top and center those so that they look good. And I'm going to go to the top and even grab those and say, let's make those things bold so they kind of stand out. And now I'm going to blow my screen up bigger so you can see it pretty well. And so where did I get then this 0.39, what is that number? 0.3989. 0.3989.
Isn't that your equation plugged in when x is 0?
That's exactly right. That's my equation. I'm just using my equation to plug that in to get all the answers that I need. So let's see, let me just try that out here. If you bust out, just to slow down and kind of make sure you understand this, we got to quit here because we're only just getting introduced to this. But I think we're close enough that we can do that. So if I stick this into Desmos as we did a minute ago, I can't show this to you, but if I stick this equation into my calculator, if I even just type it out, it was 1 divided by the square root of 2 pi. 2 pi, delete. And I multiply that times e raised to the negative x squared over 2. So negative, in this case, 0 squared divided by 2. Hey, I get 0.3989. So I could even do this. I could say equals, this is what you do in Desmos, equals 1 divided by 2 pi. I'm just gonna, let's see, what am I gonna do with that? Let's see, will it, I don't think it likes pi. I think you have to say, I think you have to say 2 times pi, but then start and close a parenthesis to get that to work. Okay, they like that. So you can type 3.14159. That's okay, or type it out on your calculator if you want to. But in Excel, you say pi and then start and close a parenthesis for pi. So it's 1 divided by 2 pi, and then times, and then exponential is exp as a command. So we said exp of negative, well, in this case, 0.01 squared, or 0.1, yeah, squared, and then divided by 2. So let's see, that doesn't seem right. Oh, I forgot I put the negative in the wrong spot. The negative was outside of the squared.
Did you do the square root?
Let's see. Okay. No, I didn't do the square root. I forgot the square root over there, so I got to go type that in. So it's exp. Maybe I need parentheses around that. And the divided by 2 is not part of the squared. So I'm just making sure I've got this typed in right. And yeah, I forgot the square root. So let's go fix that. SQRT is square root. Just going to play with this until I get that formula typed in right. It's very weird to type this stuff into Excel. Let's see, do I have it right now? No, what's wrong with my formula now? Oh, nothing, it's right. Can you see that okay to steal it? Can you guys see that? Is it too small?
No, we see it. You should probably reference D3 for 0.01. That way you can just drag it over.
Nice. That's my next move. So it's 1 equals 1 divided by the square root of 2 pi. Had to open and close parentheses. And then E, annoyingly, is not E raised to a power, it's just EXP. So it's like EXP times something or EXP of something, and it's negative the number squared. Now, to Connor's point, rather than typing 0.01 in here, wouldn't it be a lot better to say, to reference cell D3 there? Because if I do that, then if I drag it over, then this new cell references E3. And so I just got that for free. Does that make sense? So start playing around with this. We'll pick it up there tomorrow. But what I'm really doing here is just I'm plugging the numbers into the equation. I'm just trying to write them all down. This is what Simpson's rule is, right? We just need a bunch of numbers and write them all down, except for when we're doing this by hand, we can only have like 6 numbers. But what I want to do here is have a whole bunch more numbers. So
on the x-axis, are those the deviations?
Yeah, so you're reading my mind. No. So down this axis is 0.1, and that goes all the way down to, I'll just drag it down a little bit for now. And let me call those bold just so they stand out, and I'm going to center them and move them away a little bit. So this part of this is the table where all, this is where all the numbers are that I'm interested in. So I'm going to color those, I don't know, yellow for right now. And so what this represents is not, and you might notice that the answer that you see sitting here and the answer that you see sitting here are the same. But just this is an example, what does this location mean? Well, because there's a 0.5 over there on the left and a 0.03 over here, this actually represents x equals 0.53. Does that make sense? Like that's what I want to be plugging in, is x is 0.53. So effectively, these are your x's. So this is x is 0, x is 0.1, x is 0.02, x is 0.03. And then I plugged all of these into the formula to get my answers. And so this represents then not x is 0.01, but I'm looking to the left, x is 0.11. I'm sort of adding them together. Does that make sense? So I've got to plug in x is 0.11, and you're like, what does this represent? Well, this is x's, well, over on the left is 1.2, up here is 0.08. So this one represents x equals 1.28. So the question is, how can I fill this table up with all of those answers when plugged in? In other words, all those y values, that yellow page is a whole bunch of y values. How can I fill that whole table up and let Excel do a lot of the work for me? That's kind of the idea. So I'll let you think about that some, but that'll give us a start on it.
Thanks for explaining that. I've never seen a table set up like tenths and hundredths like that.
Yeah, so what this is a way of getting a ton of answers. And so if we can get this, I made it yellow, but if we can make this yellow table, and notice I pointed this out right here. Notice that red box says it's f of 1.68. What is that? Oh, there's the 1.6 and there's the 0.08. Okay, so that's 1.68 plugged into this equation up here, and then there's the answer that comes out. That's the y coordinate of that Simpson's rule. And so what we really have is, well, hundreds of y values here. And so then these last 2 columns are where we're going to use the Simpson's rule to kind of add them all up and get a really accurate answer for kind of the area under that curve, so that then we can come up with these percentages. And notice that red one right there, 0.3413, that's notice it lands at 1. In other words, this is 1 standard deviation. If I add up every single one of these values here, multiplied by 1s and 4s and 2s, and I add all of them up, cumulative sum, to that point, from 0 to 1, I have 34% there. And that's exactly what this table down here says it should be 34.3413. We should get that answer if we add all of the, notice this red graph here, it's every single number added up. Notice that's from 0 to 1, and I chose to go crazy and make the change of x 0.01. So if you have all the numbers from 0 to 1 with 0.01s, that makes sense. That's 100 numbers, actually 101. It's 101 numbers, and I'm going to plug all of that into Simpson's rule and come up with that area without ever having to be able to take an integral. And so this table was very hard fought for people that didn't have calculators a long time ago. And it's actually calculus that creates this table. And stat students are using this without maybe understanding calculus and how it works. And so we're just going to try to create that with Simpson's rule. And I'm going to help you with all of the Excel stuff. I'm not assuming you've ever had Excel at all. So I'll help you with that stuff. So I'm hoping next time when we get together or tomorrow that we just kind of play with this and we're kind of do it together. I mean, in the end, you'll end up getting this right because you ask me questions and we play around with it until you get it to work as well. So for those of you that are a little more computer minded, the question really just becomes, how am I going to get to these next rows? Like this row here, let's go down to this one. That row there, I'd like to plug in 0.53, but it's like I don't have a 0.53. So could I somehow plug in, like for X, could I plug in like this number plus this number somehow? Like that's how I'd plug it in. Like, I guess that would be cell B9 plus cell F3. Is there some way I could like plug that in and get it to do it for me, if you will? Would it actually help to have this formula like sitting up in some other cell up here? Could I have this cell off-site, like maybe over here, and then have this cell plugged into it? So that's what we're gonna play with together tomorrow. Because again, I'd like to teach you some Excel. It's kind of cool to understand how powerful this program really is, like what a page full of cells can do. Anyway, I got to shut up. It's way too late. We'll pick this up tomorrow. You don't need to work on it all between now and then, but if you want to play around with it a little bit between now and then, what I show you tomorrow might stand out as like, oh, that's totally cool. I didn't think of that. All right, get yourself out of here if you didn't do that 10 minutes ago.
I had 2 questions.
Yeah.
One, I sent you an email. I just want to make sure you got my quiz.
I did. Yep, I saw that. This morning. I got it.
Okay, good. And then the other thing is, with the table, I don't know if I put in something wrong, but my numbers are slightly different than yours for the top row.
Yeah, let's take a look at that. I'm saving my saving the sheet so that I can pick it up tomorrow and help you. Let's see. So you're saying you didn't get that number, right? Or some of these?
Yeah, my numbers don't perfectly follow the same. So I don't know if I did something wrong. Oh yeah, okay, I see the problem.
You do? Okay.
Yeah, I just had my negative in the wrong spot.
Yeah, I had it inside the parenthesis a minute ago, and when you square a negative, it turns into a positive, and I was getting it wrong because I had the negative in the wrong location. So yeah, you should be stealing that.
I think it'll be, yeah, it looks like it 6. Yeah, it looks like it matches now.
Sweet. Okay.
Thanks.
Good question. Keep going. Who else?
I saw the graded in my open math for the quiz, and I don't know why. I guess I don't have a printer right now, so I guess I just forgot to scroll all the way down. I didn't even see number 10, but I turned it in I did it like the first 30 minutes of class, and I just emailed it to you.
Great. Okay, I'll put it in there. I had a feeling that was the case. You weren't the only one who did that, by the way.
Sorry.
Yeah, no worries. You watch me make mistakes every day, right?
Rarely, maybe.
Yeah, I noticed you asked about question 9 on my quiz, and I did forget to include that with my document, so I scanned it in this morning, and I can show it to you if you're still willing to add those points.
I am, yeah. You send it to me? Yeah, send it to me. I'll send it to me an email or whatever, and I'll get it in there.
Okay.
If I made no mistakes, I could hold you guys to a higher standard, but you're gonna do that. No worries. Can survive that.
Have a good day.
You do the same.
I'll throw out one more quick question then. For the project, so we want, as we go down the rows, we want the X values to be like the 0.01 plus the 0.1.
Yeah, that's exactly right.
Okay, because I was just like trying to figure out exactly if those were both X values or if they got put in a different way.
Yeah, see, the problem with this is we got like 300 numbers because we said, hey, let's figure out the area all the way out to 3. Well, if I say we're going to go all the way out to 3 and we go by 0.01 each time, that's actually 300 numbers. In other words, we're going to have 300 numbers in Simpson's rule. And so like, how are we going to get those 300 numbers written down? Well, in order to fit it all on a chart that you could put in a book, I kind of need it to be a rectangle. I don't want it like a long strip. It would actually be easier if we just drag that to the right, clear out to 300. So I have this single strip that went clear out to 300 to the right. It'd be easier to do that, but you wouldn't be able to print that and put it in a book. And so the question is there some way we could get all 300 of those numbers in a nice tighter little rectangle that we could actually at least see all of them? And that's the thing that makes such a pain. So anyway, I'll show you that tomorrow. I'll show you how we can pull that off. We don't have to, we're done actually. We can fill the whole table up now. I just have to show you a couple of cool Excel tricks about how to get it to read the correct number, if you will, and then we'll have it.
All right, thank you.
Mm-hmm.
See you tomorrow.
Okay, see you tomorrow.